So in general, non-convex optimization problems are generally very difficult to solve, and there are some rare exceptions. So the concept is that they either cannot find, there are two problems with it. So here there are two problems with non-convex problems. So one, they require a long computation time. So the more complicated or the more non-convex the problem becomes, the longer computation time it requires. And again, the second thing is it doesn't guarantee that it will find the optimal solution. So for fast algorithms exist for local optimization, but in this case, it will be a local solution around the initial point. So for instance, from the calculus classes. So for instance, we are trying to minimize the function f. So this is a local optima here, and this is a local optima here. So this is a global optima, both local and global optima, local and global. But however, in this case, this point is basically just a local optima. So it's not a global optima. So if this function is non-convex, basically, then the algorithm may terminate at this local optima. And the termination point doesn't guarantee to be a global optimal point. That's why we mean by saying that the non-convex problems is not guaranteed to be optimally solved. And again, for global optimization, the worst case complexity grows exponentially with the problem size. So that's quite problematic. So in non-convex problem, most of the non-convex problems belong to a category called in computer science NP hard. And in this case, there are very difficult problems for those of you know. And in this case, the worst case complexity grows exponentially with the problem size in most cases. Okay, so let's look at another example quickly. So this example is a lamp illumination problem. So in this case, assume that there are n lamps illuminating n small flat patches. So in this case, there are n small flat patches, and there are basically m lamps, and we try to basically achieve a desired illumination on all patches with bounded lamp powers. So in this case, the lamp powers are bounded. So each lamp has a maximum power that it can produce. And we want to achieve a desired illumination at the points, small patches. So for instance, this is a 1 point. So just a sec. So this is a 1 point. So this is another point. By using these lamps, we try to achieve a desired illumination with bounded lamp powers. So that will be the goal of this problem. So in this case, basically the intensity at each patch depends on the lamp powers. So we have these PJs, which are the lamp powers, and IKJs are basically coefficients which are predetermined related to the showing the density or the lamp intensity at given locations. So in this case, the problem formulation is given here. And in this case, one assumption is that the illumination is perceived logarithmically by the eye. And in this case, the good formulation becomes here. And in this case, basically the intensity IK at each K point, there are K basically n patches where K is from 1 to the n. At each point is related to the power by using this formula, where Pj is the power for the jth source, which we have m sources. For each source, we have at most P max illumination here, where Pj is smaller than P max, and J is from 1 up to the m. And again, in this case, we'll basically try to maximize basically K, the maximum intensity, and minimize the maximum intensity at the patch locations. And in this case, the difference is basically log intensity K minus log intensity density, destination. So which is the minimum intensity we need to find in the destination. And again, there are many ways to solve this problem. So this is, in this case, Again, we can use a heuristic, like if you don't know an optimization or if you're not aware of these optimization techniques, one technique is a heuristic techniques, like such as assume that you use a uniform power and try different values of P uniformly for each P, and then see which one is basically satisfies or minimize the objective function. So that's kind of a heuristic approach for basically try to find different P's. And maybe you can use a binary search like things for P values, going on left or right for different P values. And you try to find the best solution. And again, for least square kind of formulation perspective, and then this is the formulation. Again, for each K location, we have intensity K, which is derived from the powers of different lamp sources. And this is minus intensity destination, and it's squared. And again, this difference should be minimized. So we try to basically find the densities as close as possible to their destination densities. And in this case, the variables are both L's, L from Ln, which will be the, I from In, which is the intensity of these patches from 1 to the n. And we have m power sources, and another set of variables are P1 up to the Pm. And in this case, this is the variable for the m sources. And in this case, again, we solve for this, and if any of the Pj is larger than Pmax, which is the maximum of these constraints, so which is the maximum power each lamp can satisfy, we make it P, which clip it, or if it's basically smaller than 0, we make it 0. Because since we don't have such constraints here, each power in the solution can be either greater than Pmax or it can be less than 0. And in this case, we basically transform those variables to either P or 0 if it's smaller than 0 or if it's greater than Pmax. And again, we didn't add these constraints here because this is not a least square problem. So if we know about the linear programming, then we approximate the problem as follows. So in this case, since these constraints, the maximum power constraints, where Pj is greater than 0 and smaller than Pmax is a linear constraint, we add it here. So this is, this is a linear constraint. Pmax is given for all P's, linear constraint. And in this case, this can be partitioned into two constraints. So for each Pj, they are greater than 0, and each J, for each power source J, its power is smaller or equal than Pmax. And again, the intensity of location K is defined similarly as in the other formulation. And in this case, instead of basically the squared power, we take it's the difference as in here, with the absolute difference. And again, this absolute difference can be turned into linear program. So it doesn't look as LP at first, but this is actually an LP. So this constraint, basically intensity K minus intensity destination, can be replaced by something like Y, for instance, YK. And in this case, YK is greater than IK minus I destination. And in this case, YK, since it's an absolute value, it will be greater than I destination minus IK. So this is the IK minus I destination multiplied by -1. And in this case, YK will be greater than all of them. And in this case, this max is also expressed as a linear constraint, such as Y. And in this case, Y will be greater than Y1. That will be another constraint. Y will be greater than Y2. It goes on like this, where Y will be greater than Yn. So even though this problem doesn't look like a linear program, it is actually a linear program. So this is the linear program. And in this case, this is how the problem looks like after transformation. Does anyone have any questions? Okay, so if no questions, then I'm continuing. So if we know more about again, for linear programming, maybe let me repeat. So in this case, we have these linear constraints here, 0, pj, p max, and they can be turned into linear constraints as in here. So the linear constraint is in two linear constraints per each j. So pj is greater than 0, and pj is smaller or equal than p max. So these are the two constraints. So this is ik is already a linear constraint, and the objective function, which doesn't look linear, is actually a linear. So what happens is that for each ik minus destination absolute value, we define a variable called yk, which is a temporary variable. And this yk is greater than ik minus I destination, and yk is greater than I destination minus ik. Since this is an absolute norm, so it should be greater than both the function itself as well as its negation. And so that it will be the positive value among its negation and itself. And again, since here we have different k's and it's the maximum among of them, here the objective function becomes minimize y, where y is greater than y1, y2, and yn, where we have basically y1, y2, yn defined for each of these yk expressions. So this is the linear programming. And again, if you know about the convex optimization, so we may actually formulate it as a convex optimization as well. So that will be a different formulation. As I told you, the problem can be formulated in many ways, depending on our knowledge. So again, if you look at the constraints, the intensity K is again linear function of power, as you see here. Again, 0 is pj, or the power of j source is greater than 0, as well as it's smaller or equal than p max. Again, these are similar to the constraints. And the objective function is slightly different. In objective functions, we have an h function where h is either the variable itself or 1 divided by variable. So in this case, we try to minimize the difference between ik and I destination. And instead of taking the minus operation, we can also divide both of them, such that if the division is basically closer to the 1, then that will be ideal. And if the division is greater than 1, then that's not what we want. So we try to make the division as close as 1 as possible, in which case, which is satisfied by this h function, where h is max u and 1 divided by u. So in this case, it's the maximum of either lk L destination or L destination lk. L destination lk, which is 1 minus u. And in this case, that will be an objective function. And again, it's a bit difficult to show here, but this is convex as well. So again, there might be additional constraints to this problem. So for instance, does adding the following constraints below complicate the problem? For instance, basically, if we add the first constraint, no more than half of the total power is in 10 lamps, then basically this doesn't complicate the problems. But if we add the fact that no more than half of the lamps are on, basically pj are greater than 0, this becomes almost like L0 norm constraint. So again, this is a bit detailed. This becomes like L0 norm. And in this case, L0 norm will make the problem NP hard. And it will make the problem more difficult.